Okay, let's look at this. This is November 2020, paper 1, only the multiple choice questions from paper 1. 1.1, the rate of change of momentum of an object. Now, whenever you see this rate of change, you know we are dividing by time. So this is mv over t, okay? The rate of change of momentum of an object is equal to, if you don't know your definitions, yes, you will have to do something about this. If you know your definitions, it says state Newton's second law of motion in terms of momentum. The net force acting on an object is equal to the rate of change of momentum of the object. So the answer is B if you don't know it. But if you want to work it out, you know that the rate of change of momentum, okay, and momentum is P or mv, over the rate, which is change in time. I've now got mass times velocity over time, which is the same as mass times acceleration, which we all know is equal to F net. So if you didn't remember your definitions, just use some logic. Momentum is mv, rate of means divide by time. So I've got mv over change in time, which is the same as m times acceleration, which is the net force. Now 1.2, it says to you, the gravitational acceleration on the surface of planet X with mass m and radius r is little g. The gravitational acceleration on the surface of planet Y with mass 2m and radius a half r is. So you have to work this out. You can't just think this in your head. If you want to think it in your head, you know that if we increase the mass, then the force will get bigger. Okay, so this will make a bigger g. A big mass gives you a big g. And a small radius also gives you a big G because it is an inverse square law. So anything that's smaller than G, we are going to get rid of. So these two we've immediately got rid of. And then we're going to use the formula. So we've got this formula, F equals G M1 M2 over R squared. And if we're lucky on the data sheet, we also have little g equals big G M over R squared. But if we don't have the second formula, this F over here is actually Fg, which is mg, which is equal to g m1 m2 over r squared. But this is the same as that mass, and the other mass will be the mass of the planet. So you can actually derive this formula yourself if you want to, but that's not that helpful right now. What we want to do is we want to figure out by how much is this g getting bigger. So we take this second formula, g equals gm over r squared, and we go little g equals big G, which we're going to ignore because it's not changing, it's a constant, over 2 times 2m because the mass doubled, okay? And then this is over a half, oh, look what I've done, a half r, the r must be in the brackets, all squared, okay? So now let's think about this denominator of a half r squared. This is the same as saying g equals g 2m divided by, and a half r squared, a half times a half. Think about this, people. A half times a half is a quarter. So this is g 2m divided by a quarter r squared, which is the same as saying g 2m times 4 over r squared. So now the r squared will be the same from the other equation. The m is the same and the g is the same. So on the right hand side of the equation, I've put a 2 times 4, which is 8. So the answer is D, 8g, because you've got to make the left hand side equal the right hand side, and we multiplied the right hand side by 8. So in terms of little g, it will be times by 8. Then let's have a look at the next question. 1.3. The graph below shows how one of the physical quantities associated with an object in free fall changes with time t. The label on the y-axis is emitted. Ignore air friction. So, if you think about this, you can suddenly be having an exciting moment and think, oh, look, that looks like the acceleration graph, because we know for an object in free fall, the displacement graph often looks like the shape of the object in motion. The velocity time graph is always either a vertical line up or, a vertical, she says, a line with a positive gradient or a line with a negative gradient, like that, depending on whether you say up is positive or down is positive, okay? And then we know that if we say up is positive, we end up with a straight acceleration time graph like this. So we could have looked at this and thought, woohoo, let's look for acceleration in the answer. And if we look for acceleration in the answer, it's not there. So let's have a think. What is velocity? Velocity is the change in position with the change in time. So for an object in free fall, okay, we are thinking about one of our projectiles here. There's no ways the velocity is not changing, because as a ball goes upwards, the velocity decreases. It gets to maximum height, the velocity is 0. And as it goes down, the velocity increases. So there's no ways that the velocity is constant like is drawn on the graph. There's no ways the position is constant, because an object in free fall is moving. Weight. What is weight? Weight is your mass times the acceleration due to gravity. Does the acceleration due to gravity change? No. This is a constant on our lovely planet. Is the mass going to massively change while we're throwing the object? No, so this is also going to be constant. So the answer here is C, the weight, because the mass of the object is not changing and the acceleration due to gravity is not changing. And we can rule out D, the momentum, because the momentum is mv, and while I agree the mass is going to stay constant for a projectile, the velocity will change all the time. So the momentum graph would actually look basically the same shape as the velocity time graph. And then let's go to the next question if I click the correct button. It says, a ball of mass m falling vertically downwards hits the floor at a speed v and bounces vertically upwards at a speed of 0.75 v. So let's draw this. Here comes the little ball here, and it goes down to the floor here, and it hits the floor at a speed v, and then it bounces upwards at 0.75 v. So the first thing we know is that this was an inelastic collision, but this does not seem to be helpful with anything going on with the question. So it says, which one of the following combinations regarding the change in momentum of the ball during the collision is correct? Now, the first thing that we have to remember is that momentum is a vector, okay? Momentum is a vector. It has a magnitude and direction. So the change in momentum, delta P, is going to be mvf minus mvi, because that's what delta means, final minus initial. So the m is not going to change, okay? So I have 0.75 v minus 1v over here, okay? How have I said this? When I said this, did I actually give a vector direction here? I have not given a vector direction, so I will get the wrong answer unless I describe a vector direction. So if I say down is positive, okay, what happens to this equation over here? It becomes m equals 0.75 v minus, because it's always final minus initial, down is positive 1v. What have I done? This is negative and this is positive, okay? Because the 0.75 is up, this will be a negative vector. So now I actually have minus 0,75 minus 1, okay, which is going to give me minus 1,75. These are both V's. Okay, I'm being lazy here. Don't be lazy. I've got minus 1,75 mv. That is my change in momentum. Okay, so I need something with this magnitude. Can you see this is the correct magnitude? And according to my vector direction, it says down is positive. So this one, if this is a negative sign, it must be upwards, because down is positive, which means up is negative. So therefore, this upwards and the 1,75 mv go together. So the answer is C. So look here. Delta P equals mvf minus mvi, which equals, take the mass out because it's a common factor, vf minus vi. We said that down is positive, so vf is upwards. This is the vf over here, and this is the vi on this side. So if down is positive, this is minus 0,75 minus positive 1v. So a minus and a plus makes a minus. I get m minus 0,75 minus 1v. Look at me leaving these v's out. Okay, and there you will, that will be how you get your answer. Now it says to you 1.5, the base SI unit of the physical quantity work is. Well, we know that we measure work in joules, okay, but we are not using joules because it's not a base unit. Remember, there's only those 7 base units. So to work this out, what are we going to do? We're going to find any formula that we have for work, okay. So I kind of like W net equals delta EK. So I'm going to use the formula for EK, because EK is a half mv squared, okay? So this is what the formula is. The left-hand side must equal the right-hand side. So the left-hand side is measured in joules. The right-hand side is also measured in joules. So either one will give me a unit for work. So a half does not have a unit. It's just a number. Mass we measure in kilograms. Velocity is the rate of change of displacement. Okay, so V equals delta X over delta T. And the units for this, we measure displacement in meters and we measure time in seconds. So I have got V squared, so it's meters over seconds times meters over seconds. So what have I got here? The half has got no unit. I've got kg, I've got meters times meters, and they are over seconds squared, which we write as seconds to the minus 2. So this corresponds with the answer C. So if you don't know the SI unit, you take any formula for whatever they're asking and substitute the units for all of the variables in the formula. You can also do it with F delta X cos theta, which is also the formula for work. Okay, F is MA, delta X cos theta. Theta doesn't have a unit. Mass is measured in kilograms. Acceleration is meters per second, and delta X is in meters. So you can see I'm ending up with the same thing. Cos theta, no unit. We're going to ignore it. Kg, meter, second squared. It gives you the same answer, just a different route. Now, this one's quite interesting. This is the Doppler effect question. It says the siren of a police car, so here is my police, moving in front of a truck, here is my truck, emits sound waves of frequency F. So here is my thing emitting sound waves. Both vehicles are traveling at the same constant velocity, okay? The frequency of the sound heard by the driver of the truck is, and the answer here is A. Why is the answer A? Remember what the Doppler effect definition says, and especially that old definition that they sometimes let you use in the question paper. If you want to have the Doppler effect, you have to have two objects moving relative to each other, okay? And so what is actually this word relative mean? It means the one must be faster or slower. Either there's a stationary listener and a moving vehicle, or a stationary listener and a moving source, or a stationary source and a moving listener that are moving relative to each other. But if you are moving at the same velocity, the distance between you never gets bigger or smaller, you never get closer or further apart, and therefore the sound waves reach you exactly as they are propagated. So you hear exactly the same frequency. It's only when there is relative motion that you can get the Doppler effect. Something must be approaching or moving further from something else. Now here's the electrostatics question. Two identical metal spheres, P and R, on insulated stands carry different charges. The spheres are brought into contact and separated again. This is from grade 10, the law of conservation of charge, that says in any physical process, the net charge in an isolated system is conserved. And it comes down to this formula, Q nu equals Q1 plus Q2 over 2, okay, which we could be putting here as QP plus QR over 2. The charge is basically averaging out. It says to you, if the charge on sphere R after separation is Q, the charge on sphere P, it is going to be exactly the same. It is also going to be Q. This is grade 10 physics. In an isolated system, the net charge is conserved, which I always say it is just averaging out. The charge averages out. So if you've got three objects, you would take this formula and divide by 3. Okay, this one is the electromagnetics. An AC generator generates a current with a frequency of 50 hertz. What is frequency? Frequency is the number of cycles per second, or the number of waves passing a point in a second, but with electricity it will be your cycles. Now it says to you the number of times that the peak current is produced in 1 second is. Let's think about what this question is asking. It's asking you for the peak current. And I did have a bit of a wonder when I saw this question for the first time. If you look at electricity generation with AC, you end up with this sine curve like this. And technically, this is I max, and this one is minus I max. But in actual fact, these are both the peak current, because in terms of the appliance using it, this will be the peak usage. So in every one wave, can you see this is 1 lambda? Here is, look at me drawing that line so terribly. Here is another 1 lambda. In every one wave, I have 2 peaks, a positive peak and a negative peak. So if it's 50 hertz, then I've got 50 waves. Can you see I've drawn a whole 3 waves over here? Imagine 50 in 1 second, okay? So it's 50 waves per second, but each wave has a positive peak and a negative peak. So the answer here is D, because 50 times 2 equals 100. There are 100 maxima every second. One is a positive maxima, one is a negative maximum. Okay, it says in the circuit below, the battery has an internal resistance little r and an EMF E. A variable resistor R is connected in the circuit, and the ammeter and voltmeter register readings. This is basically your practical, so you should know what you are doing. It says to you the resistance of the variable resistor R is increased now. Well, we know that R is inversely proportional to current. So if we increase R, we decrease the current, okay? So it says, which one of the following combinations is the correct representation on the change in the readings on the ammeter and voltmeter as the resistance R is increased? So if we are increasing the external resistance R, the ammeter reading is going to decrease, which leaves us with options A and D. But if we want to think about this, we need to think a little bit harder, because in grade 12 we have this internal resistance issue here. Previously, if you didn't think about it, the answer would be a lot easier. So we know that the EMF of the battery is fixed, okay? And little r is also fixed, okay? So what are we doing here? We are increasing the value of this one, okay? So if we do this, we know the ammeter reading is going to go down. But the EMF is equal to the V external plus the V internal, okay? So if we think about this, and remember the V internal is sometimes called the V lost, but they don't like you to call it the V lost, okay? So let's put numbers here to make this easier. If we say to you, we are playing with 12 volts EMF, okay? And say I have a fixed internal resistance of 2 ohms, okay? Then if I say 12 equals IR plus 2, okay? If my current decreases, okay, then what's going to happen is that my V internal is going to be a smaller number times by this 2 here, okay? So then my V internal is going to decrease, okay? But my 12 here is fixed. My EMF is fixed. So if my V internal is going to go down, then my V external is going to go up. So the answer here becomes A, okay? So do it with numbers, okay? Knowing that this E is fixed. If you can't understand the logic, you say E is fixed and you give it some number that's easy to work with, and you give little r, which is also fixed, a number that's easy to work with. So you say this is 12 and this is 2. What happens if my internal resistance, say initially, my external resistance, 12 equals my I, and I just assign this a random value, yeah? This value is 1 and this value is 2. Then in this circuit, 12 is going to be my current times 3. Then here my current is going to be 12 divided by 3, 4 amps. And now we say, well, this is a scenario in the question, increase the big R. My 12 is fixed. We don't know what's the current yet. I'm going to increase my R. I can increase my R from 1 to 2. My little r is fixed. So now what's going to happen to my current here? It's my current times 4 equals 12. So my current here is going to turn into 3 amps. So you can see if we increase the big R, the current definitely decreases, okay? But if we want to know what's the voltmeter reading, it is the voltmeter reading on the second one, and then we're just going to go E equals V external times I plus V internal times I. And if you put the numbers back in here again with this 3 amps that you've just calculated, you will work out that this number gets bigger, and because these two are in series, a series circuit is a potential divider, and it must add up to the EMF of the cell. So it works out that the voltmeter reading will also increase. Just if you're confused, still pause the video and go do it with your own numbers, and you will find out it is always true. Now 1.10, this is the photoelectric effect. The sodium cathode of a photocell is irradiated with UV light as shown in the diagram below. The ammeter registers a current. So we know for certain here that this is over the threshold frequency. UV is over the threshold frequency because if it was not over the threshold frequency, then no electrons would be emitted. So what do we need to do to increase the ammeter reading? So what is the ammeter reading? The ammeter is reading current, okay? What is current? It is the rate of flow of charge, okay? So current is the rate of flow of charge, which is Q over time, okay? You remember this formula is on your data sheet. Current equals Q over delta T. So if we want the current to increase, okay, we are doing it per second. We have to increase the amount of charge, okay? So how do we increase the amount of charge? Remember, what is causing the current? Electrons are causing the current. So the only way to increase the amount of charge is to increase the electrons per unit time. How do we increase the number of electrons? We have to increase the intensity of the ultraviolet light, okay? The only way to increase the number of electrons is to increase the intensity of ultraviolet light, because remember, a light bulb is emitting these little packets of energy. Look at my lovely light bulb here. It emits little packets of energy like this, the quanta, and every quanta is for one electron. So one quantum, one electron. So if you want to get more electrons to pop off, you have to emit more quanta. If you change the frequency of the ultraviolet light, okay, you will just make the electrons come out with more EK. This one increases the kinetic energy of each electron, but it's not going to give more electrons for your ammeter to count. Remember, an ammeter is just like an electron counter. And so these two, C and D, have the same effect. If you put a cathode with a lower work function, remember the E is WO plus EK max. So by lowering the work function, all that's going to happen is you're going to increase the maximum energy of the electron, but you will not make more electrons pass per unit time.